Have you ever gazed at the night sky and wondered about its mysteries? Today, we embark on a thrilling journey back in time to the very beginning of our universe. Fasten your seatbelts as we dive into the heart of the Big Bang, the moment of creation. From that infinitesimal point, we'll witness the universe expand and cool, its fundamental forces taking shape. Our journey will take us through eras with exotic names like the Planck Epoch and the Quark Epoch. So join us as we venture into the early universe and uncover the secrets of our existence. Imagine a stage where the laws of physics as we know them break down. This is the universe in its infancy, a realm of unimaginable heat and density. At the heart of this cosmic drama lies the Big Bang, the singularity that marked the beginning of everything. From this primordial inferno, the universe embarks on an extraordinary journey of expansion and cooling. The very fabric of space-time stretches, carrying with it the seeds of galaxies, stars and planets yet to be born. The stage is set, and the curtain is about to rise on the grand spectacle of the early universe. Our journey begins at the very moment of the Big Bang. Picture all of the matter and energy in the universe concentrated into a single infinitesimal point, a singularity. The Big Bang wasn't an explosion, it was the rapid expansion of space itself. This concept might seem mind-boggling, but it's supported by a wealth of observational evidence. The Big Bang model provides the best explanation for the universe we observe today, a universe still expanding from that initial moment of creation. As the universe expanded, it also cooled, much like the air rushing out of a deflating balloon. Within the first fraction of a second, the universe underwent a period of rapid cooling and expansion known as inflation. This rapid expansion smoothed out any initial irregularities in the universe, creating the remarkably uniform cosmos we observe today. As the universe cooled further, energy began to condense into matter, following Einstein's famous equation E equals mc squared. The stage was set for the formation of the first atoms, the building blocks of stars, galaxies, and ultimately life itself. The early universe was a dynamic and ever-changing place. One of the most important phase transitions occurred around 380,000 years after the Big Bang, known as recombination. Before recombination, the universe was filled with a hot, ionized plasma of protons, electrons, and photons. However, as the universe cooled, electrons combined with protons to form neutral hydrogen atoms, making the universe transparent to light. These photons now form the cosmic microwave background radiation, a faint afterglow of the Big Bang that we can still detect today. Our journey into the early universe takes us now to the Planck Epoch, a period so early in the universe's history that it's difficult even to comprehend. We're talking about a time just 10 to the minus 43rd seconds after the Big Bang. At this incredibly small scale, the universe was governed by the extreme conditions of quantum gravity. Some physicists believe that at this scale, space and time become fuzzy and ill-defined, perhaps even breaking down into discrete units like pixels on a computer screen. Exploring the Planck Epoch is like peering into the very heart of creation, a place where the laws of physics as we know them dissolve into a sea of uncertainty. As the universe expanded and cooled from the Planck Epoch, it entered the grand unification epoch. During this time, the single unified force that governed the Planck Epoch began to separate, giving rise to the distinct forces we observe today. The first force to break away was gravity, becoming a distinct force in its own right. The remaining forces, the strong nuclear force, the weak nuclear force, and electromagnetism, remained unified for a brief period. The separation of the fundamental forces laid the groundwork for the formation of particles, the emergence of stars and galaxies, and ultimately, the conditions necessary for life to arise. As the grand unification epoch drew to a close, the universe underwent a period of exponential expansion known as inflation. During this incredibly brief period, the universe expanded at a mind-boggling rate, increasing in size by a factor of at least 10 to the power of 26. Inflation explains why the universe appears so remarkably uniform on a large scale, with the same temperature and density in all directions. Quantum fluctuations, tiny ripples in the fabric of space-time, were stretched to enormous sizes during inflation, creating regions of slightly higher and lower density. These density fluctuations served as the seeds for the formation of galaxies and galaxy clusters, the vast cosmic structures we observe today. As quickly as it began, inflation came to an end. The universe continued to expand and cool, but at a much slower, more leisurely pace compared to the breakneck speed of inflation. The end of inflation marked a dramatic slowdown in the universe's expansion. The inflaton field, having decayed, released its energy into a sea of particles and radiation, creating a universe brimming with potential. Tiny quantum fluctuations, stretched to enormous sizes during inflation, created regions of slightly higher and lower density, forming the seeds of galaxies, stars, and planets yet to be born. As the universe continued to cool, it entered the Quark Epoch. This epoch marked a time when the universe was dominated by a sea of quarks, the fundamental building blocks of protons and neutrons. These quarks, along with gluons, swirled about in a hot, dense plasma, constantly colliding and interacting. The Quark Epoch was a crucial period for the evolution of the universe because it set the stage for the formation of protons and neutrons, the building blocks of atomic nuclei. The next stage in this journey would see the formation of protons and neutrons, paving the way for the emergence of atoms and the first elements. Section 3. A sea of quarks and gluons. The Quark Epoch featured quark-gluon plasma, or QGP. In QGP, quarks and gluons exist freely, forming a cosmic soup. This state existed just after the Big Bang and in high-energy collisions. Imagine quarks and gluons as dancers moving freely. QGP has extremely high energy density and behaves like a nearly perfect fluid. Studying QGP helps us understand the universe's fundamental forces. The Hadron Epoch, a universe of heavy particles. As the universe expanded and cooled, it marked the beginning of the Hadron Epoch. This epoch, from 10 to the negative 6 seconds to 1 second after the Big Bang, saw a dramatic cosmic shift. The universe transitioned from quarks and gluons to heavier particles, known as hadrons. Imagine a cosmic kitchen where intense heat cooled enough for complex structures to form. Quarks began to bind together under the strong nuclear force, forming hadrons. Among these hadrons were protons and neutrons, the building blocks of atomic nuclei. These particles would eventually form the nuclei of atoms, laying the foundation for stars and galaxies. Section 2. From quarks to hadrons, the dawn of protons and neutrons. The transition from a quark-gluon plasma to a hadron-dominated universe was gradual, driven by the cooling cosmos. As the universe expanded and cooled, the strong nuclear force began to influence larger distances. The strong force guided quarks into pairs and triplets, forming protons and neutrons. The formation of protons and neutrons marked a crucial turning point. These particles provided the building blocks for atomic nuclei. The proton-to-neutron ratio influenced the abundance of elements and the formation of stars and galaxies. Following the Hadron Epoch, the universe entered the lepton epoch, lasting from 1 second to 3 minutes after the Big Bang. This period was dominated by leptons, including electrons, muons, taus, and neutrinos interacting through weak nuclear force and electromagnetism. Imagine a vast cosmic ocean teeming with diverse marine life. Hadrons, like large sea creatures, swam among smaller, agile leptons, darting and swirling through the cosmic depths. The lepton epoch was a time of intense activity, with leptons constantly created and destroyed. Leptons and antiparticles annihilated each other, converting mass into photons. Photons could also produce lepton-antilepton pairs, a process known as pair production. Neutrinos played an important role, streaming through the cosmos, carrying energy and influencing nucleosynthesis. The formation of atomic nuclei followed. The lepton epoch, though brief, set the stage for the next phase, when light elements were forged in the Big Bang. As the universe cooled and expanded, it reached the era of nucleosynthesis. This period, from 3 to 20 minutes after the Big Bang, forged the light elements. The universe transformed from protons and neutrons into atomic nuclei. Protons and neutrons fused, forming hydrogen, helium, and trace elements. By the end, 25% of the universe's mass was helium, 75% hydrogen. Following nucleosynthesis, the universe entered the Photon Epoch. This epoch, from 20 minutes to 380,000 years after the Big Bang, saw photons dominate. The universe was a hot, dense soup of photons, electrons, protons, and atomic nuclei. Imagine a cosmic ballroom ablaze with light, where photons zipped and swirled. The universe was opaque like a thick fog, with photons constantly scattered by free electrons. This red-shifting of photons formed the cosmic microwave background, a faint afterglow of the Big Bang. The cosmic symphony of light and matter. The Photon Epoch was a time of intense interplay between light and matter, shaping the early universe. Photons collided with electrons, exerting pressure that counteracted gravity. Imagine a cosmic tug-of-war, with gravity pulling inward and radiation pressure pushing outward. This balance influenced the growth of density fluctuations leading to galaxies. As the universe expanded and cooled, the energy density of photons decreased. This shift allowed gravity to pull matter into larger structures. The Photon Epoch set the stage for the structures we observe today. The universe emerges from the fog. As the universe expanded and cooled, it reached a critical turning point known as recombination. Around 380,000 years after the Big Bang, the universe transitioned from opaque to transparent. Imagine a dense fog lifting, revealing a hidden landscape. Before recombination, the universe was a sea of charged particles and photons. Electrons combined with protons, forming neutral hydrogen atoms. The fog lifted and photons traveled freely through the cosmos. The cosmic microwave background, an echo from the early universe. Recombination had a profound consequence for our understanding of the early universe. Photons, once trapped in the early universe, now travel through space. These photons provide a snapshot of the universe at 380,000 years old. This snapshot is what we observe today as the cosmic microwave background, or CMB. The CMB is a faint afterglow of the Big Bang, permeating all of space. Embedded within it are tiny temperature fluctuations, seeds of galaxies. The CMB provides vital information about the early universe and tests cosmological models. Section 3, The Dark Ages, a universe in waiting. After the brilliant flash of recombination, the universe entered the Dark Ages. This epoch, lasting from 380,000 years to a few hundred million years after the Big Bang, was dark. The universe was a vast, cold expanse of neutral hydrogen gas. Matter slowly coalesced under gravity. Imagine a stage after a grand performance, lights dimmed, curtains drawn. The universe had entered a quieter phase. Despite its name, the Dark Ages were not devoid of activity. The seeds of structure, sown during inflation, continued to grow under gravity. Regions of higher density attracted more matter, forming gas clouds that would collapse into stars and galaxies. The Dark Ages were a time of gestation, preparing for the next grand act in the cosmic drama. The universe was evolving, setting the stage for light and the formation of structures that would eventually give rise to life. The darkness would give way to the light of the first stars, marking the end of the Dark Ages and the dawn of a new era. the cosmic dawn. After hundreds of millions of years of darkness, the universe transformed. Gravity drew together clouds of hydrogen and helium gas. These remnants of the Big Bang needed a spark for nuclear fusion. Imagine a vast, dark expanse, a cosmic sea of gas. Pockets of gas clumped together, drawn by gravity. As clumps grew, their cores heated, nearing nuclear fusion. The first stars were cosmic pioneers, devoid of heavy elements. Known as population 3 stars, they were mostly hydrogen and helium. Their birth marked the transition from darkness to light, the first light ionized gas transforming the universe forever. Section 2, Giants of the Early Universe, population 3 stars. Population 3 stars were giants, hundreds of times more massive than our Sun. Born in a universe with ideal conditions for rapid star formation, the absence of heavy elements allowed these stars to grow to extraordinary sizes. Imagine giant clouds of gas collapsing, birthing massive, short-lived stars. These stars, blazing with blue-white light, ionized the surrounding hydrogen gas. Their immense mass led to a short lifespan, burning through their fuel in just a few million years. Their deaths were dramatic supernova explosions, seeding the cosmos with the first heavy elements. From darkness to light, the epoch of reionization. The first star's birth and deaths ushered in the epoch of reionization. This epoch, from 400 million to 1 billion years after the Big Bang, transformed the universe. Intense radiation from early stars ionized the neutral hydrogen gas. This process made the universe transparent, setting the stage for galaxy formation. Section 1. A universe transformed. Our journey through the early universe has taken us from the unimaginable heat and density of the Big Bang to the emergence of the first stars and galaxies. We have witnessed the universe expand and cool, transforming from a sea of elementary particles into a cosmos teeming with structure and complexity. The early universe was a time of dramatic change, a period of rapid evolution and transformation. In the span of just a few hundred million years, the universe transitioned from a hot, dense soup of quarks and gluons to a cosmos filled with the first stars and galaxies, their light illuminating the darkness and setting in motion the processes that would shape the universe we observe today. Section 2. Our cosmic heritage. The early universe is not just a distant chapter in cosmic history, it is our cosmic heritage, the foundation upon which our very existence rests. The elements that make up our bodies, the planets and the stars, were all forged in the crucible of the Big Bang and the fiery furnaces of the first stars. As we gaze up at the night sky, we are looking back in time, witnessing the light from stars and galaxies that has traveled for billions of years to reach our eyes. The faint glow of the cosmic microwave background whispers to us of a time when the universe was young, hot, and rapidly expanding. The study of the early universe is a journey of discovery, a quest to understand our cosmic origins and unravel the mysteries of our existence. It is a testament to the power of human curiosity and our relentless pursuit of knowledge. As we continue to explore the cosmos with ever more powerful telescopes and sophisticated instruments, we will undoubtedly make new discoveries that will challenge our understanding of the early universe and inspire us to ask even deeper questions about the nature of reality itself. The journey through the early universe is a journey that continues to this day, a journey that reminds us of the interconnectedness of all things and the profound beauty and wonder of the cosmos we inhabit.
Like and subscribe to start your journey today.